Hey everyone, welcome back to The Explainer. Today we're taking some pretty complex economic theories and turning them into practical blueprints for growth. We're literally unpacking the underlying mechanics of how to scale a business efficiently. We're going to look at the actual rules of production that dictate how small local operations manage to morph into massive global empires without just, collapsing under their own weight. It's a truly fascinating look under the hood of corporate growth, and I promise you, by the end of this, you're going to see business expansion in a completely different light.
I want you to really keep this question in the back of your mind as we go. Because, let's be real, avoiding bankruptcy while blowing up your factory size or scaling your tech startup, it isn't just luck. It's pure math. Growth just for the sake of growth can actually destroy a business if the underlying variables aren't balanced perfectly. Overhiring, overbuilding, mistiming your capital investments, those things will drain cash reserves overnight. So today, we're tracking down that exact mathematical balancing point where expansion drives maximum profit.
All right, here's our roadmap for today. We'll be hitting the production function, the laws of returns to scale, isoquants and isocosts, the properties of isoquants, the least cost combination, and tying it all together with economies of scale. Let's get right into it.
Section 1. The production function. To build a rock-solid foundation, we first absolutely have to understand the difference between being stuck with what we currently have and having total operational flexibility. Now, the most interesting thing to consider here is the timeline. The long-run horizon is where true scaling actually happens, because all of your inputs, labor, capital, the whole shebang, become completely variable ingredients in your production recipe. Think about running a coffee shop. In the short run, your hands are kind of tied. You've got fixed factors, right? A super expensive espresso machine, a tight lease on a tiny building. You can really only tweak variable things, like throwing more baristas behind the counter. But honestly, if you cram 10 baristas behind one machine, you are definitely not getting more coffee. In the long run, though, those fixed constraints completely vanish. You can lease a massive warehouse, buy a whole fleet of roasting machines, and hire entirely new divisions of workers.
Moving to Section 2, Laws of Returns to Scale. Once we actually have control over all our ingredients in that long-run scenario, we need to know exactly what happens when we increase them all proportionately.
Let's say we bump up all our inputs by a certain percentage, which we'll just call P. And let's say our total output increases by a resulting percentage, H. You basically have three possible realities here. First is constant returns to scale, where H perfectly equals P. You increase inputs by 50%, your output grows by exactly 50%. It scales perfectly. The second possibility is increasing returns to scale. Now this is the absolute dream scenario. You boost your inputs by 50%, but your output just explodes by, say, 80% because of some newfound efficiencies. And the third is diminishing returns to scale, where H is actually less than P. You pour 50% more investment in, but the output awkwardly lags behind, maybe only growing by 20%. Not great.
Section 3. Isoquants and isocosts. To actually navigate these possible returns, we need some visual maps. We need tools to measure the constant trade-off between human labor and capital machines.
Think of an isoquant as your equal quantity line. It literally maps out every single possible combination of workers and machines that'll produce exactly 100 units of your product. It defines your technological trade-offs. For example, you might be able to hit your 100-unit target with a multi-million-dollar, highly automated factory and just a tiny staff of 3 technicians. Or you could hit that exact same 100-unit target with a massive manual workforce utilizing just a few basic, inexpensive tools.
So as you slide along this curve, you're constantly changing your mix of capital and labor while your total output stays totally locked in. Each higher parallel curve just represents a higher level of overall output, producing 200 units, then 300 units, you get the idea. And here's a really brilliant visual shortcut for mapping growth. If you were to draw a straight line, a ray, starting from the zero origin in the bottom left and slicing straight outward across these curves, the physical distance between the curves along that line actually tells you your returns to scale. If the gaps between the curves get smaller and smaller as you move outward, boom, you are experiencing increasing returns. If the gaps get wider and wider, you're hitting diminishing returns. It's a fascinating way to visualize the math.
But, we don't have infinite money. Which brings us to the isocost line. This is our strict budget boundary. While an isoquant shows you what is technically possible to produce, the isocost line acts as a ruthless financial reality check. It shows you exactly what combinations of labor and capital you can actually afford to buy with the cash you have on hand.
The absolutely crucial point to grasp here is that the downward slope of this straight budget line precisely represents the ratio of the price of labor to the price of capital. Let's consider a typical budget boundary, maybe line MN. If your total budget stays the exact same, but the minimum wage for labor suddenly doubles, your ability to hire workers shrinks drastically, right? The bottom anchor of your budget line would just shift way inward. The entire slope is relentlessly dictated by the market prices of your inputs.
Section 4. Properties of isoquants. Before we mash these two tools together, our technological capabilities and our financial budget, we have to respect the properties of our isoquants. These aren't just arbitrary squiggles, they're governed by strict economic laws.
Let's run through these super quick. First, they slope downward. Why? Because increasing one input naturally means you have to reduce the other if you want to maintain that constant, equal level of output. Secondly, they never ever intersect. That completely defies logic. If they crossed, it would mean one single combination of labor and capital could somehow simultaneously produce two entirely different levels of total output. No way. And finally, they're convex, meaning they bow inward toward the origin. This happens because of something called the diminishing marginal rate of technical substitution. Simply put, human workers and machines are imperfect substitutes. If you take away a machine, you might need 2 humans to replace it. Take away another machine, now you need 5 humans to make up the difference, because the factory floor is getting crowded and inefficient. It creates that bowed shape.
Section 5. The least cost combination. This right here is where our scaling journey hits its climax. We know what we want to produce, and we know what we can afford. Now we overlay them to find absolute mathematical perfection.
When you overlay these, you're looking for one specific spot, a single point of tangency. We'll call it point P. This is the holy grail, where your budget perfectly aligns with your production targets. Think about the production curves that sit above your straight budget line. You simply do not have the cash for them. They're financially impossible. And what about the spots where your budget line just slices right through lower production curves? Sure, you can afford it, but you are leaving money on the table. You're not maximizing your output. Point P, that exact spot where the straight line literally just kisses the curve without crossing it, is the one and only spot where you minimize your total cost to production while maximizing your total output.
And that perfectly sets up this rule. It brilliantly illustrates the magic moment where the physical rate at which you can swap machines for humans on the factory floor exactly matches the ratio of their market prices. When those two slopes are identical, you're no longer fighting against the market or your technology. You've found the ultimate blueprint for operational efficiency.
Finally, Section 6, Economies of Scale. Tying this all back to the real world, how does finding this tangency point help us understand massive business growth?
Well, when you rapidly increase your scale, it essentially boils down to a constant, vicious battle. On one side, you have economies of scale, where getting bigger gives you massive cost advantages. On the other side, you have diseconomies of scale, where getting too big, too fast actually starts hurting you. Economies of scale are those sweet bulk purchasing discounts, highly specialized divisions of labor, or leveraging advanced robotics across millions of units. But they are constantly fighting against diseconomies. Imagine a nimble startup morphing into a corporate behemoth. Suddenly, you're dealing with massive bureaucratic bottlenecks, global communication failures, and endless layers of middle management that just slow every decision down.
As you scale up, if your structural advantages can actually outpace those operational disadvantages, you hit the coveted increasing returns to scale. This is that magical zone we talked about earlier where your total output grows in a much larger proportion than your inputs. It's what happens when expanding your scale fundamentally makes you leaner and faster. But a quick warning, eventually every massive firm will see those diseconomies creep up. It drags them down into constant or even diminishing returns where growth actually becomes a liability rather than an asset.
So I'm going to leave you with this final thought to ponder the next time a massive corporate expansion dominates the news. Are they carefully hitting that perfect mathematical tangent point, unlocking economies of scale, and riding the wave of increasing returns? Or are they just expanding blindly, walking straight into the trap of diminishing returns, entirely suffocated by the diseconomies of getting too big, too fast? Understanding this delicate balance between inputs, outputs, and scale, that is the ultimate key to sustainable business growth. Thanks so much for joining me on this explainer. Keep analyzing, keep optimizing, and we'll see you next time.